Welcome back, everybody. This is our video solution to problem 3 from Quiz 5, Spring 2023, Math 302 at Cal State Fullerton. And we are going to talk about Euclid's Lemma in this video. So first thing, we just have to state it. Hey, we could do that, right? We learned the actual statement. So Euclid's Lemma tells us, all right, so if P is a prime, and A and B are integers such that P divides A times B, then P divides A or P divides B. Okay, that's simple. There are some slight variations that you could give. For example, sometimes instead of saying then either one of these holds, you might assume also that one of them does not hold, like, oh, P does not divide A, and you conclude P divides B. All right. In the homework, we gave a generalization of this to where we didn't have to have a prime anymore, but we had to assume that whatever we did put here was relatively prime to one of the factors. And if that was true, then you would know that that number would divide the other factor. All right, but this is Euclid's lemma. And now we're asked to give an example to show why the hypothesis, okay, so the hypothesis here, right, is this piece, right, everything before the then, assumes that the divisor, okay, yes, P is the divisor, is prime. Yeah, why do we need this to be prime, right? Well, I just said we don't, right, as long as it was relatively prime to one of the factors, but we can build a counterexample if P is not prime, and you don't have this relative primeness condition. So here's going to be our counterexample, and there's, of course, infinitely many counterexamples we could write down. So all I have to do, in fact, is pick a number, right? Pick a number, and here's what I would say is don't pick a prime. Now, as soon as I know it's not a prime, I know it should have a couple of different factors at least, right? Prime factors, maybe. So how about I pick, I don't know, how about the number 10? Okay. Now, can I think of a number that 10 divides where it's not going to divide either one of them individually? Now, 10 is equal to 2 times 5. So what I need to do is come up with a number here and a number here where one of them has a 2 as a factor and the other has a 5, but the first one doesn't have a 5 and the second one doesn't have a 2, because then 10 can't divide either one of them. All right, so for example here, how about I put the number 8, right? That's divisible by 2. And here I'll put the number, how about 75? Okay, that's 25 by 3. Okay, fine. So 8 times 75, which is equal to, now let's see, if you double 75, you get 150. Doubled again, you get 300. Doubled again, you get 600. So all right, so this is equal to 600. Yes, obviously 10 does divide 600, right? This is 60 times 10. But 10 does not divide 8, and 10 does not divide 75. Now, you might say, did you work too hard to build that counterexample? Heck yeah, I worked too hard, right? What if I had just written down 10 divides 10, right? This is equal to 2 times 5, right? 10 certainly divides 10. It does not divide 2. It does not divide 5. Okay. It is very, very easy, ultimately, to make as many of these kind of counterexamples as you want. Okay, and this is why you want the hypothesis to say that P is prime, or in this extended version, at least it has to be relatively prime to one of the factors, so that all of the factors of your divisor show up in only one of the factors on the right. All right, and there we go. We'll see you next time when we talk about the fundamental theorem of arithmetic.